Hello, welcome to the lecture on BMS safety, and thank you for joining me in the transition to sustainable energy. This lecture on safety is split into 4 video clips. In the first video, we'll discuss key considerations for large lithium-ion batteries as in cars or associated with home solar, and how they relate to industry standards. Next, we'll cover some general safety concepts applicable to any design where design for safety is critical, though my examples will all feature battery management. If you're already familiar with fault trees and DFMEA, you can skip videos 3 and 4. If you're looking to design a BMS for a cell phone, toy drone, skateboard, or similarly small device, the content in this lecture is largely overkill. Okay, let's dive in. Safety encompasses many aspects. Let's talk about how they fit together for a lithium-ion battery. We have choices related to the inherent safety of the cells. We've talked about how NMC cells may go exothermic, while LFP cells are considered less prone to this. We also should consider manufacturing quality, since that affects how often cells may fail and initiate a safety event in the field. You might recall how GM intended to address the root cause underlying the recall of the Chevy Bolt by pushing on its cell supplier to improve manufacturing quality. Pack construction also entails safety-related decisions. For example, some packs incorporate propagation barriers to ensure that if one cell goes exothermic, the behavior does not spread to its neighbors. All large packs should include mindful design around venting, so if a cell suffers an internal short, the gases that it produces exit the pack with the least possible collateral damage. Electrical engineering design usually includes the sensors which underlie system controls decisions. It also includes circuits that control the battery switches and possibly a pyro fuse. The design may incorporate hardware-only protections, such as chips which will detect a cell overvoltage and open a contactor without firmware control. The electromechanical design of battery switches and fuses can fall to either the electrical or the mechanical team. The software is responsible for key safety decisions, such as when to allow operation, when sensor readings indicate a safety-related fault, when to cease operation, and so on. The software may run system diagnostics critical to detecting faults. The software may interleave safety-related functions with other functions. Testing is really important to ensuring that the implementation achieves the intent. Testing should check both the hardware and the software. It is absolutely critical to catch design mistakes and incorrect assumptions. Manufacturing quality can affect safety. The FMEA part of safety analysis incorporates failure rate, which it calls occurrence. If a component fails at a much higher rate than estimated in FMEA, the results of the analysis may suggest that a system is safer than it actually is. The best design differs by application. The impact of a cell phone battery fire is very different from that of a truck battery fire, and the impact of an e-bike unexpectedly shutting down differs from a hospital backup battery shutting down. Consequently, a sensible safety architecture will be different for each of these applications. And team organization matters. Oftentimes, these various aspects of safety belong to different teams, different groups of people. How well those teams communicate will affect the overall safety of the product. For automotive and home energy batteries, safety is guided to some extent by standards. Let's touch upon those standards and some corresponding terms. The term functional safety refers to the automated part of a safety system. It includes the circuits and the software that respond to a safety-related event without human intervention. If we go back to our overview slide, functional safety encompasses the automated parts. So that's the sensors that collect safety-related information, the microcontroller and other chips that monitor the sensors, the software that interprets what's going on, the actuators that implement safety-related functions, and the testing of those components. Several industries use functional safety standards. ISO26262 is the functional safety standard for cars. Most major car manufacturers require that their suppliers comply with ISO 26262. So, for example, when I worked at Continental, we complied with ISO 26262. Fault tree analysis and FMEA, two safety tools introduced in this lecture, are required as part of ISO 26262 compliance. Some Silicon Valley car companies favor a different approach and do not comply with ISO 26262. They apply a more holistic ad hoc approach, selectively using some of the tools shared with ISO 26262, but perhaps omitting some of the more bureaucratic paperwork and relying on cross-team communication for broader coverage. That can work well for a very vertically integrated company, meaning one that manufactures its own subcomponents and integrates them into larger systems and owns everything in this slide. But there's a good reason why many automotive manufacturers require ISO 26262. Many car makers use components built by other companies, and ISO 26262 serves as reassurance that safety was well considered in the making of these subcomponents. One caveat around ISO 26262 is that it's an involved enough process that it is often done by a dedicated safety expert, adding one more team to the org chart. A term you will hear often in the context of functional safety and ISO 26262 is ASIL. It stands for Automotive Safety Integrity Level. It's used to classify how important to safety a particular component is. In this slide, we see some examples. The rear lights are classified as ASIL A, meaning that the rear lights failing is a safety risk, but a low one. The rear brake lights are ASIL B, meaning their failure poses a slightly larger safety concern. ASIL D has the highest safety repercussions and includes inadvertent airbag deployment, since this could abruptly interrupt the driver's ability to control the vehicle. Battery electronics are considered ASIL D as well. One last term that I introduce is FTTI, or the Fault Tolerant Time Interval. This is the time period from the occurrence of a fault to the violation of a safety goal. In other words, this is how long the system has to respond to a fault before something unsafe might happen. For example, if we have an overcurrent event, such as a short in the motor, the FTTI would be derived by calculating how long the system can withstand the overcurrent, and that would be used to specify how quickly the system must respond. This FTTI might drive a fuse specification, for example. Okay, let's move on to a different standard. UL1973 applies to stationary batteries, such as you might find in a home with solar panels. This standard includes similar system safety analysis as ISO 26262, and then, additionally, a multitude of other requirements and tests. One part I especially like is the internal fire exposure test, which requires initiating thermal runaway in one cell and observing for 1 hour, requiring no propagation of fire and no explosion. I believe that in large enough scale production, cell defects will occur. A large enough population of batteries will experience the occasional internal short due to a latent defect. So, I like the requirement of designing and testing for this. Okay, so UL 1973 for stationary batteries seems broader than ISO 26262 for automotive. Is that sensible? Car safety obviously matters when driving. If the battery experiences a significant fault, there's risk of injury from a battery fire, or an accident due to loss of power, and also risk of stranding the occupants in an inherently unsafe location. On the bright side, we can rely on at least one capable adult, since presumably the car has a driver who is awake and aware and capable of decision-making. In case of a fire, for example, the driver can decide to get everyone out in a hurry. In case of a fuse disconnecting the battery, the driver may be able to steer the coasting car onto the shoulder. Also, we should consider the case of a parked car. If the car is parked outdoors, a battery failure resulting in loss of power likely carries minimal repercussions. But if the car is parked inside the attached garage of a wood frame home, a common scenario in the United States, a battery fire is a pretty scary outcome. The occupants of a home may be asleep. They may be elderly or very young and unable to exit the premises without assistance. and financially, the value of a house greatly exceeds that of the car itself. On the other hand, if a fault causes the contactors or fuse to open, the consequent loss of power is unlikely to result in a safety risk in a parked car. The risks associated with stationary battery failure are similar to a car parked in a garage. Note that the risks may increase for applications where the battery is the sole energy source, such as an off-grid home, or if the battery powers critical equipment such as medical devices. In other words, in some applications, power off is not a safe state. What do you think now? Which safety standard warrants more rigor? An interesting consideration is whether to implement safety responses in hardware or in firmware. The safety standards require validation of the whole system and revalidation when any changes are made. A software implementation typically has the BMS microcontroller running multiple functions, including safety. Any change to the codebase requires revalidating all safety functions. This architecture entails a schedule dependency between the implementation of code unrelated to safety and safety validation. An all-hardware implementation entails a different sort of schedule dependency, requiring that safety limits be defined quite early in the design process. Both system-level limits and state of charge estimation are appealing to finalize late in design, when the system is nearly complete, since both are best defined after a thorough characterization of the whole system. Attempting hybrid approach entails firmware configurable hardware. A BMS ASIC may incorporate analog comparators and switch drivers to implement hardware-only safety responses, but the threshold for those comparators, or the reference voltage, is configurable. The microcontroller incorporates code to configure the hardware thresholds. The idea is that we can validate the hardware-only safety responses before the microcontroller software is complete. The caveat is that changes in the configuration code may escape validation. In summary, safety encompasses many systems developed by many teams. Excellent safety requires excellent collaboration processes. ISO26262 and UL1973 are the safety standards for large automotive batteries and home energy storage, respectively. The need for safety varies by application, with automotive and home energy batteries sharing many characteristics. Safety validation is a schedule challenge. Since we must verify the final design, learnings from validation feed into the design process quite late. This is the end of video clip 1. Please continue the safety lecture with video clip 2.